Hey guys, this is Mrs. Harbin, and we are doing a little mini unit in advanced math. So this is unit 2A, and we are just going back over how to graph lines, how to write equations of lines, how to find the slope and the intercept from a line. So looking only at linear equations. And today we're going to look at parallel and perpendicular lines. Before we do that, let's do a quick lesson opener. Take a look at these equations and state the slope of each linear equation. And out to the right, draw a little sketch of what that line would look like. If you don't remember, we have Mr. Slope Face here. When our line is going in this direction, it's a positive slope. When our line is going downhill, it's a negative slope. When our line is completely horizontal, it's a zero slope. So it's got like a little mouth there with zeros. And when our line is going straight up and down like you're diving off the edge of a cliff, that is actually undefined. So we put that little U there. And hopefully that little picture helps you remember what the different slopes look like. So let's state the slope. We know that when our equation is in this form, y equals mx plus b, our slope is this number here in front of our x term. And so our slope here, this first one is -4, and that is a downward slope. So our sketch would look something like this. For the second one, our slope is, well, there's no x value. Y equals -3, which means our slope is 0. There's no x value at all. And our sketch would look like this, just a nice horizontal line. And in x equals 7, well, x equals 7 is a completely vertical line, which means our slope is undefined. All right, let's take a look at this. Describe the graph of each function. So very similar to what we looked at before, what would the graph look like? If x is equal to 7, we know that our graph would look like this, and we would describe that as vertical. It would be a vertical line. And y equals -3. If y is equal to -3 with no slope whatsoever, our line looks like this, which is a horizontal line. And so that's how we would describe those two graphs. Our biblical integration for this unit is that God provided 4 different gospel accounts in His holy word that provide us different insights into the same story, basically the life of Christ and the coming of this new covenant. Graphing equations helps us to see written information from a different perspective. For you, you might be the kind of person that prefers to see information in a chart, with your input on one side and your output on the other. Or maybe you would like to see a bar graph or a pie graph, or maybe you just want to see mountains of data not organized at all in any kind of form, but as raw data. But what graphing allows us to do, it allows us to see trends, it allows us to make predictions, it allows us to see what is usually just lists of numbers as something visual. It's a visual representative that can allow us to see information in a different perspective. Our lesson objective for today is that you, the student, will write the equation of a line using point-slope form, which might be new to some of you, using a point on a line in the equation of a line that is either parallel or perpendicular to it. So we've looked at slope-intercept form, that y equals mx plus b. We've looked at standard form. Let me write these out here. Slope-intercept form is y equals mx plus b. It's called slope-intercept because we have both the slope and the y-intercept identified in that formula. Standard form is ax plus by equals c. That is the standard equation of a line. And today we're going to look at point-slope form. We'll also talk about what parallel and perpendicular lines have to do with slope. So just to review, I wrote it on the previous slide as well, the standard form for a linear equation is ax plus by equals c. Slope-intercept form is y equals mx plus b, with m telling us what our slope is and b identifying our y-intercept. A third way that you can write a linear equation is by using point-slope form. And point-slope form is useful when you know a point on the line and you know the slope. Point-slope form. In this case, m would be our slope, just like in slope-intercept form, and the y1 and x1 would be the two x's and y's, or the 2 points that we know. The variables, x and y, that don't have the subnumbers with them would just stay x and y. Like in slope-intercept form, they just stayed x and y. So point-slope form of a line provides an alternative method of determining the equation of a line from the slope in any given point. If you remember, when we knew points earlier, what we did, we started with slope-intercept, and we found the slope. Let's say our slope was 3. So we plugged in our 3 here. And then when we knew particular points, maybe our point was, 1, 1, we plugged in our points here and we solved for B. Once we knew what B was, we then went back and plugged in that information to put our whole formula in slope-intercept form. Point-slope form is just another way to find that same information, just a little bit different because you don't have to solve for B. You don't have to take that step here. So this is what it looks like in point-slope form. So let's say you're told, not necessarily the slope, but you're told the equation of a line passing through these 2 points, -5, 2, and 3, -4. We can use that information to find the slope, and we're going to do that by labeling our x1, y1, sorry, that doesn't really look like an x there, and x2, y2. And we know the equation for slope, which we're going to write every single time just to make sure we don't mess it up, is y2 minus y1 over x2 minus x1. When we sub in, make sure that you're subbing in with parentheses, again, to protect those negatives. So y2 is -4, and y1 is 2, so -4 minus 2 over x2, which is 3, minus x1, -5. So that's the information we're going to plug in, and then we are going to simplify. When we do that, we find that our slope is -6 over 8, which simplifies to -3/4. So that is our first step. Find the slope for point slope. Once we know the slope, which is -3/4, we're then going to plug in what we know into this formula. Y minus y1 equals m times x minus x1. Where it says y1, we write our y1. Now we could use either one of these. We could use this as our x and our y. It doesn't matter. For this particular one, this set of points was used, but you could use either one as long as you use the x and the y that go together. So we've plugged in a -4 here. For our m, we've plugged in -3/4, and for our x coordinate that we know, we've plugged in 3. At this point, we do need to use the distributive property to simplify. So we get y plus 4 equals -3/4 x. Plus 9/4. Don't forget, when you multiply these two negatives, you do get a positive. We still haven't finished yet because now we need to get this +4 gone so that y is just by itself. So we're going to subtract 4 from the left, and whatever we do from the left, we also have to do from the right. And we get y equals -3/4 x minus 7/4. Don't forget that when you are subtracting 4 here, you've got to have your fractions with common denominators. So -4 is the same thing as -16/4, and 9/4 minus 16/4 is at -7/4. That's where that came from. So this is just a different way to get your equation into slope-intercept form. When you know the slope and you know a point, you can use the point-slope formula. Now, if we wanted to change that to standard form, we know that we want our x and y on the same side. We don't want to lead with a negative coefficient, and we don't want any fractions. So the first thing that we can do is multiply everything up here by 4. That will get rid of the fractions on the bottom. And that turns our whole equation into 4y equals -3x minus 7. We then want to add 3x to our right because we don't want it on the right side. And whatever we do to the right, we do to the left as well. So we've got 3x plus 4y equals -7, and that is in standard form. Let's take a look at some definitions. Our second part of our objective today was dealing with parallel and perpendicular lines. So just as a reminder, parallel lines are lines in the same plane that have no points in common. They run side by side like a pair of railroad tracks. They never cross. We know that the graphs of linear equations are parallel if they have the same slope but different intercepts. If they had different slopes, eventually they would cross. Even if they were just slightly different, maybe they run parallel for a really long time, but if they have just a slightly different slope, eventually they will cross. Parallel lines do not cross because they have the same slope, but you can see that they cross the y-intercept at two different places. So parallel lines, same slope, but different y-intercepts. Because we know that parallel lines have the same slope, we can write equations of the lines that we know are parallel based on that information. Let's take a look at these two equations. We have 3x minus y equals 6 and negative 9x plus 3y equals 12. We're going to rewrite both of those in y equals mx plus b format. We find that the equation on the left has a slope of 3 with an intercept of 0, negative 6. The equation on the right has a slope of 3 also, but its y-intercept is 0, 4. So we see two lines with identical slopes. They both have a slope of 3, but with different y-intercepts. That tells us that these are parallel lines. And if we wanted to check that, we could graph those, plug and chug some values, and we would see that they are indeed parallel. Now let's use that information to write that the slope-intercept form of an equation of the line parallel to 4x plus 3y equals 17, and it must pass through this point, negative 5, 9. Well, the important piece of information here is that it's parallel. And if it's parallel to this line, then it must have the same slope as this line. So they must be equal. If we know the slope of this line, then we know the slope of our parallel line. So let's start by determining the slope of our first line. There are two different ways that we can do this. We can actually use this little formula, negative a over b. Don't forget, a is our Sorry for that pause there. I realize there is a problem with this slide and I can't go back and fix it here. So a is the coefficient in front of the x value, so that's 4, and b is our coefficient in front of our y value, so that's 3. So this should be negative 4 over 3. Another way that we can find the slope is by putting it into y equals mx plus b. If we do that, we get 3y equals negative 4x plus 17. And when we divide both sides by 3, we see that our slope is y equals negative 4 thirds x plus 17 thirds. So we can use this little trick here, negative a over b, or we can put it into y equals mx plus b format to find the slope. Now, I have a feeling that that number is wrong on all the following sides, so we'll have to go ahead and change that manually. So negative 4 over 3 is our slope. We then want to use that slope and the point that we've been given, this negative 5, 9, to plug it into Pointslope form. All right, oh, it is right on this side, good. So we have y minus y1 equals m times x minus x1. We plug in our slope, negative 4 thirds. We plug in our 2 points, 9 and negative 5, using parentheses to protect our negative, and then we simplify. We get y equals 9. Y minus 9 equals negative 4 thirds x minus 20 over 3. Let's get that y all on the side by itself, so we add 9 to both sides there. Remember to have a common denominator before you add or subtract fractions, and there is our equation of a parallel line passing through those 2 points. Now, perpendicular lines have a little bit different slope. Perpendicular lines meet at right angles, or 90 degrees, and their slopes are negative reciprocals of each other. The negative reciprocal of a is 1 over a. So we take this and we put it at the bottom of our fraction with 1 at the top, and we change the sign. Let's try a few negative reciprocals really quickly before we get into a slope problem. If your number is 8/5, your negative reciprocal would be negative 5 over 8. If your number is 9, your negative reciprocal would be negative 1/9. Right. Hopefully you can see here the negative reciprocals. I am quickly running out of time, so I'm going to pause the video right here and finish up this last problem in part 2.